So here's the solution to the pair quiz that we did in class number 10, where we tried to calculate how heavy an aircraft could be if we only considered the Bernoulli lift effect on the wing that was described. So the wing was described, each wing 7.2 meters long into the fuselage here, had a straight line width of 1.6 meters. That would be along the bottom of the wing where the wing is straight. And then the top of the wing, we were told, has a length that is 1.15% longer than the bottom wing length. And what that's going to do is it's going to cause the velocity of the air over the top of the wing to travel at a higher velocity than the velocity under the bottom of the wing. Now, the bottom of the wing is straight, so the velocity as the air flies by the bottom of the wing is just at 70 meters per second as the air just shoots by at whatever speed the plane is going. But air that comes and hits the top side of the wing is going to have to go around and come back, and it's going to have to travel a longer distance. And you can see that in a certain sense, in order for mass conservation to continue, that is mass in equals mass out, that air is going to have to travel faster. Otherwise, it won't, get out at the same rate that this air is getting out. But of course, it's all entering at the same rate. So that's an argument for why this is faster. Now, technically, it wouldn't have to be 15% faster right at the top of the wing. So this is an approximation. It could be a lot. It could be just a little bit faster over a larger segment up here in the sort of above the wing space. But that's not what really happens. Viscous effects on the wing and the effect of the wing here are confined to a very narrow layer on the top of the wing. So these effects of the wing causing speed up in the flow are confined to a very, very thin layer near the top of the wing. So while it's not exactly accurate to say that it actually has to be 15% increase, that is a good approximation, and certainly the one we'll continue to use when doing this kind of analysis. So the wing is 15% longer. That means the velocity has to be 15% faster in order for that air to get over the top of the wing in the same amount of time that the air going under the wing gets under the wing. All right, so that's what we got there. So we know the velocities on the top and the bottom. Now it's time to go ahead and write the Bernoulli equation. So the Bernoulli equation says for the top and the bottom of the wing that P top over rho plus V squared top over 2 is going to have to be equal to P bottom over rho plus V bottom squared over 2. There's no change in Z here. The Z, I'll just try to get this to focus a little better. The Z is, not changing as we go across the wing, essentially, very, very small changes. So that's not going to be the issue. We know the P on the bottom of the wing is going to just be atmospheric pressure. And we know the V bottom, is that 70 meters per second. We just figured out what V top was. So we know these three. We don't know rho yet. So the first question we could ask is this an incompressible flow? Well, if it's not incompressible flow, we can't use Bernoulli in this form. So that's the first thing. It is incompressible. Why? Well, because the velocity of the plane is 70 meters per second. The velocity over the top of the wing is 80 meters per second. We know that we can treat airflow as incompressible if we're within, below or around 100 meters per second, maybe up to 120 meters per second. So we're still below that, even with this, reasonably fast flying aircraft. So we can use incompressible flow, which means we can use the Bernoulli equation, and we can treat density as being constant. So if we can find density anywhere in the flow, we can treat that as density everywhere in the flow. We know out in the free stream that we were told in the problem that T is equal to 12 degrees Celsius and P was equal to 95,000 pascals. So that's our temperature and our pressure. And if we have that temperature and pressure, we can go ahead and calculate a density. So rho is equal to P over RT. R is going to be 287 joules per kilogram Kelvin, using joules instead of kilojoules so that I have my units are consistent. Rho is equal to 95,000 pascals over 287 joules kilogram Kelvin. I translate that into Kelvin. That's 12 plus 273 is 285 Kelvin. So that gives me an answer of rho is equal to, I believe, 1.6 kilograms per meter cube. Is it now? It's not 1.6. It's a little too low. 1.16 is equal to 1.16 kilograms per meter cubed. So there's my density. I can use that in both equations. So now I have that P top, which is the one I don't know, is equal to P bottom, which I do know, 95,000 as given to me here, plus rho, which I do know now, equal to V bottom, sorry, it's not equal to, but times V bottom, V top squared over 2. So there's my Bernoulli equation that's going to give me the top pressure. I plug in all my numbers for that. I get P top is equal to 95,000 newtons per meter squared plus 1.16 over 2 times 70 squared minus 80.5 squared. And when you crunch the numbers on that, you get that the top pressure is equal to 95,000 newtons per meter squared minus 917 newtons per meter squared. And of course, just do that subtraction. I get that the top pressure is equal to 94,083 newtons per meter squared. All right, so there's my top pressure. I've got my bottom pressure is 95,000. So that's going to lead to an upward force. So you've got to convert these pressures into forces. Of course, we know that force in general is equal to pressure times the area it's acting on. It also acts only normal to the surface. So one thing that, so on the bottom, this is very easy to conceptualize because the normal to the surface is directly up. So the bottom pressure is going to lead to a directly up force. That makes perfect sense. So F on the bottom is going to equal 95,000 newtons per meter squared times the area of the bottom of the wings. So the bottom of the wings, well, of course, A is equal to the length times the width. So A of the wing is equal to 7.2 meters times 1.6 meters. So that's equal to whatever the heck that is. Let's see, clear. 7.2 times 1.6 gives you 11.52 meters squared. And of course, I'm going to double that because I have two wings. So 2 wings, F up equals whatever that 23.04 meters squared. So that's my area for 2 wings. And my F up would be my F up would be that area, 23.04 meters squared times 95,000 newtons per meter squared. So that's fine. That's easy to see that that's going to be pointing directly up. The question of the F down, it did confuse some of you. It never even occurred to me, honestly, but it's going to be the same area because, and I'm going to give a whole supplementary lecture and put it online if you want to watch this, but basically, no matter what the top shape of this wing is, if you just think of the force being different here and here, the force pushing down, it's going to push down all over this surface. There's going to be a net force down. There's not going to be a net force left or right because it's going to be completely symmetric. So that's clear. That's true no matter what the shape of the wing is. So if you have a wing that's shaped a really stupid shape like this, that would be a terrible wing. But you've got your pressures acting all along here. But the only net force from all of that is going to be a downward force. So it's going to be the same calculation, the same area. That's the area that's normal to the surface, normal to the direction of interest, in this case, downward. And so it's the same area. So as I say, there will be a supplemental lecture for those of you who don't see that right away, that there's going to be a net zero in the forward and backward direction from this pressure force because it's a closed surface. And there's going to be a net downward force because the force is on, the net force from the top is going to be just net down. So we're going to go ahead and use the same area. So then that means that the lifting force is just the difference in the pressure from the bottom minus the pressure on the top. And the pressure on the top is what we have there. 94,083. And so I multiply that by the total area of the wings, that pressure difference. The total area of the wings we said was, my papers aren't very organized today, 23.04 meters squared. And that's going to give you a net lift pressure. So we calculated the F up from this. We now know how to calculate the F down from that. Just acting on the same net area, cross-sectional area, to the direction of lift. And so that comes out to be just 917 newtons per meter squared times this two areas. So that's 23.04. So that's equal to 21,127. Sorry, that wasn't written right. 21,127 newtons. So that's our lift force pointing in the upward direction because the pressure is lower at the top of the wing, it's higher at the bottom of the wing. And of course, if we want to turn that into a mass, well, that has to hold up the airplane in a gravitational field. So that's our equation there. And we can calculate that the mass is equal to 2,154 kilograms. So we can have a 2,000 kilogram plane and it will have enough lift going 70 meters per second based just on the Bernoulli effect to hold up, could be held up, provided that the upper wing surface is 15% longer than the lower wing surface. As I say, I will now record a lecture on the way that integrating that surface, the pressure over a closed surface on the top of the wing, causes a netward downward force and not a left and a right force.